Hey Adrian, how was the trip back to Korea?
It was okay.
Are you stuck without any materials?
Yeah.
So are you in an apartment or a house?
House.
Now, let me see if I can remember correctly. Your family is from Busan? Not Seoul, correct? Hello?
Our family doesn't really have a house now in Korea.
Okay, but so you're in Seoul
No, I'm in in my grandparents' house.
and your grandparents' house is in which region?
Chungcheongdo? I don't think you know.
Is it closer to the East Coast or the West Coast?
It's in the middle.
Middle. Okay, so you're quite rural. It's your grandparents' house, is it?
Yeah. I'm like very rural.
Excellent. So if you go outside, can you walk around?
No.
Like
I can't go out of the house.
You can't go around walking around the property?
What do you mean property?
Like you can't go outside and do gardening?
Well, I can go outside on like our house garden, but there's like a big gate. I can't cross that.
Yeah. So on that property, is there like a shed, tools, bits and pieces, an old radio, something like that?
I guess so.
Okay, if you can find almost all equipment that you have should have a capacitor in it.
That's not same as making a capacitor.
Yeah, but you can still do some work. So you have this, you have these, most of your electronic devices need some sort of converter to turn the alternating current into a direct current. Now, once you go through the little square AND gates and stuff, your sine wave becomes kind of like a bunch of hills. Now that's where you need a capacitor to level that out. So every one of these, ooh, that's actually quite warm. Most of those pieces of equipment should have something that turns your alternating current into a direct current. So finding a capacitor shouldn't be difficult.
Multimeter.
Yes, there are ways to check if a capacitor is working without a multimeter. See if you can figure out how to do that.
Why?
What?
Hi.
How?
Why should I need to do that? I thought that's like another level.
No, you don't need to do it. This is a real world problem. I'm giving you something that has no definite answer. If you can find a multimeter, sure, go for it. Yisul, you're in Korea as well now?
Yep.
How are you doing?
Last week was kind of terrible. Yeah. I had to go to like hospital.
All right.
Like so many times.
Ado.
Using ambulance.
Ado. So wait, why were you going to hospital?
I have throat problems, and like last week my throat became so like bad until I couldn't speak almost. So I need to get to hospital, but like I'm in quarantine, right? So the government wanted me to take ambulance so that I don't like interact with
anybody else.
Anyone.
Wow. And the hospitals are crowded, or?
No, it wasn't crowded, but I had to wait until the hospital closed so that nobody's there.
Wow.
And the doctor wanted me to come like 2 days after I went to hospital, so I had to go like multiple times last week, and I had to do like ride ambulance and it was kind of embarrassing because everyone just looked at me when I get off the ambulance like a coronavirus patient or something.
You could have tried to make it a bit more like, maybe play some hip hop or something as you come out.
It's just so terrible. It's just, yeah. I don't absolutely.
The situation isn't as good here because like right now in Korea, every people that come in from outside, they see you like literally as a corona patient. Like even though you don't have corona, they see you as corona patient, and it's so annoying.
Yeah, they just
They
hate
treat you like
everyone.
one.
Everyone from like foreign country. They're like, oh, why just coming to Korea? You just bring the virus and try to kill us.
Yeah, they're
They're literally.
so sensitive.
That's so annoying. It was
It's
so
so
terrible.
freaking annoying.
It'll be fine once you're out of quarantine. You can then go to the airports and say you're
Once
bringing
I'm out of
Korean.
quarantine, I'm
Korean.
gonna go to their office and like speak to them. Seriously. Oh my god.
I'm done. Today is the last day I'm being quarantined. I can go out tomorrow, yes.
Ah. Oh, okay. All right. Well, I'm glad that you guys are there. You're safe and everything's okay physically. I covered questions 1 and 9. I covered questions 1 and 9 with Ethan and Aiden on the last Zoom. So I want to jump into questions 14 and 16 today with you guys. All right? Okay. Let's dive right in. Share screen, whiteboard. Here we go. Okay. So to start with, the question on page 489, what is the electric potential 15 centimeters from a 4 microcoulomb point charge? Okay. So we're going to start with a 4 microcoulomb point. Nah, that's not going to work. Let's give that a red. A 4 microcoulomb point charge. And this will be positive just because of our thing. 4. Come on. 4 microcoulomb. Actually, I'm just not even going to write 4 microcoulomb. I'm going to write 4 times 10 to the negative 6 coulomb, so that we have it in the correct units. In the same way, I'm going to do the distance that we have 15 centimeters away, was it? I don't want to do text. Come on, let me do this. Thank you. So away from this, come on. Whoa, that's trippy. Okay, so instead of 15 centimeters away, I'm going to change it to the units that I want, which is 0.15 meters. Okay, so that's, I want to know what the electric potential is at this area here. Now, very, very simply, if you go back a page to 488, it'll give you a list of these equations. You can use most of them. Let's go with the one that we need to use first, which is equation 17.4. So this is where your voltage, the difference between the 2 points, the difference in electrical potential between the 2 points, not potential energy, but the potential, is equal to ED. So E is your electrical potential energy, and D is your distance. So this relates, your energy has to do with what your location is. Okay, it's like being able to make a blanket statement if you're 10 meters, 100 meters above sea level, 1,000 meters above sea level. It's that sort of reference. Okay, and the other one that you want to be looking at is VKQ on R. This basically says that your voltage is equal to Coulomb's constant by the charge over the R. And now R is radius. Now what you probably have seen is your Coulomb's law Coulomb's law has, let's go back to Coulomb's law so we can compare how we get there. So Coulomb's law is force equals to Coulomb's constant. The two charges multiplied together divided by the distance squared. Now, if you have your distance here and your electrical potential energy is there, you can turn that electrical potential energy, you can work that out from force. How do we relate work and force? Can anybody tell me how you get from force to work or work to force?
Isn't work force times, is it distance?
Yeah, that's it. Work is force over distance. So if I've got, come on.
Work is force times distance.
Yeah, if work equals force times distance, then you can start fiddling here. Because you also have Coulomb's law, which is force equals to K QQ divided by RR, R squared. How do I do squared? Okay, so you've got Coulomb's law there. You've got Coulomb's law here. You have your relationships between voltage and your electrical potential energy, which has to do with the location where that is. And then you have your voltage, which is related to Coulomb's constant. And you derive this. This is the one that you want to get to. You want to derive this from the other three equations. Okay. So basically, we can get rid of one of these by saying that as your distance becomes infinite, as your distance becomes infinite, your charge should go to 0, I think. Yeah. So if you don't have another electric charge there, you can assume that if your other charge is 0, if you get rid of the small q, then you can also get rid of one of the r's, because that r would also be fairly infinite. You're basically getting rid of a term. So you, you're not getting rid of the term, you're dividing one of the distances, so you get the, yeah, okay. I wish I had a whiteboard so I could do this much more elegantly. Anyway, moving on. What we want to use is we want to use this particular equation here. This is the one that we want to use for this particular problem. So if I know what my point charge is, and I know my distance from that point charge, and I know that the Coulomb's constant is, what is Coulomb's constant?
9 times 10 to the power of 9.
Yep. 9 times 10 to the power of 9. So we can just go straight into plug all those values in, and could somebody get me an answer for that? Yes, you may use a calculator. Of course you may use a calculator. No, move the cat away, Becca.
Did you guys get a very big number?
Yeah. 2. Can I say it now?
Yeah, go for it.
2. Whoa, 2 million?
Mm-hmm.
Yeah.
400,000.
Yeah, 400,000.
Yeah, I got 2.4 times 10 to the 11.
Well,
That's-
that's a bit bigger than ours.
That's a bit bigger. That's like a
Yeah, I think I missed. I think I put the Q in wrong.
all right. So let's go again. Let's actually run through that. So we're looking for the voltage. It's on the correct side of the thing. We have 9 times
10 to the
10
power.
to the 9.
Yeah.
Our point charge is 4 times 10 to the negative 6. Yeesh. And we are dividing that by point. Oh, it's not 0.015. I've made a mistake here. It's just 0.15. Let me just. Okay.
And it's gonna be bigger.
All right. So
What?
I know it's gonna be smaller.
Smaller.
Right? Yeah.
I got 240,000.
well, if you do it in steps, you actually save yourself a lot of problems. So
Oh, I got
divided by 1.5 gives me
400,000.
26.67.
Wait, Mr. Hendro,
Yep.
why is it that I read 0.015 meters before?
Me
Okay,
too.
never mind. Probably just Aaron.
So what's the answer?
I'm still working it out.
Yeah, it's 240,000,
Okay,
right?
If you're multiplying these two numbers together, what you can do to simplify this is you can get rid of the 9 and the 6 because they will cancel each other out. So let's have 9 times 26.67. Oh, why did I close the calculator? 9 times, oops, 98. I don't want 98. 9 times 26.67 gives me around 240. So I've got 240 here. 240, and then I just add the numbers together on the what's the word? The exponents. So that should just be 10 to the 3. Now I can make that so that the significant figure is 2.4 times, why is it not working? 2.4 times 10 to the 5, or 240,000 volts. Great. Okay. That's how I would answer that one. 240,000 volts. Now, how much charge is going to move over that 15 centimeters? If I had one electron pass over that distance, is that going to be dangerous? If I had one electron move that 15 centimeters, is that going to be at all dangerous?
Dangerous if you like, what is this distance between? Like,
Well, they're saying that the potential difference between this point charge here and 15 centimeters away, the voltage, that means the potential difference. So if this has a very high, if this is a, it just means the difference between the 2 points in terms of their, it's like you could say, if I'm 15 meters above a mountaintop, or I'm 15 meters above sea
Isn't it
level.
dangerous?
even if the voltage is high, it doesn't have to be dangerous, right?
No.
As long as the charge is low.
Yes. So
Oh.
the charges involve the number of electrons, because electrons are a set quantity of electricity.
But didn't you say one electron only?
One electron will do almost nothing. So you know the Van de Graaff ball that I was putting my hand near and getting zapped? That should be close to about, that should be measured in the millions. That 240,000 volts is getting up to that is getting up to the Van de Graaff sort of levels of potential difference. And this is completely different to when you have charge that flows normally. That's what you have in your mains power. It's different. Flowing charge is different to when you have static charge. We're still on static charge here. Now, if I was to bring that closer together, if I was to just modify this term here, if I was to turn that 15 into a smaller number and I was to add another 0 there, whoops. If I was to add another 0 there and I was to make it, instead of 15 centimeters apart, it was 1.5 centimeters apart, what would happen to my voltage?
Increase.
By how much?
Let's check.
One more 0. No, 1 more 0.
Would it increase the voltage?
1 more 0.
Sorry, if you
2.4.
increased what? The charge?
If I make the
Times 10.
if I make the distance small, what will happen? It'll multiply everything by 10, right? So I'll get another.
Yeah.
I'll get another.
0.
It'll go from 240,000 volts to 2.4 million volts.
Mm-hmm.
More like a Van de Graaff. Now, if I can get that potential difference, to 3 million volts, if I can get it to 3 million volts, what will happen to the air?
Air, like around it? Like
Yes, what happens to air? If you increase the potential difference enough, you'll see some changes.
Can you try it?
Yes, I have.
Yeah.
I've done it with a Van de Graaff machine.
What does it look like?
It would mean the
Oh.
distance would decrease.
No, the distance does not decrease. So go to page 483 just for a second. Look, and there's a table in the top right called dielectric constants at 20 degrees Celsius. You found it?
Yep.
Okay. So if I bring two objects close together and the voltage per meter is 3 times 10 to the 6, what has happened?
Page 483.
83. This is a concept called
Where-
dielectrics. If you have an insulator between two plates or two charges, that is called a dielectric because it's the insulator between these two charges. Normally it's air, but if you pass that dielectric strength, you will then turn the air into a conductor and it will zap. Okay, so you don't want to get it too close or it will zap. Mind
Is that
you,
what you were saying? Eventually, like in a car, like you're safe from lightning unless it becomes like so powerful, then it just jumps to you.
well, here's
that
the
what you're
weird
saying?
thing. The car is a conductive material. Dielectrics are almost always non-conductive materials. So what you see over on the right there, you see air, paraffin, polystyrene, vinyl, paper, quartz, oil, glass, rubber, porcelain, mica, water, strontium titanate. None of that is conductive.
But then, like, if you're in a lightning storm, then the air around you inside the car could become the dielectric, right?
Not really, because the electric charge the electrons want to travel in a medium that has easy motion. It's much easier for the electrons to move through a conductor like steel than it is to move through you.
Okay.
It'd be like having the toll road to Surabaya and the bad road to Surabaya, and they're both free. Which one do you go on?
Toll road.
That's the one. The conductors are these toll roads. All right, that's question number 14. Let's jump to question number 16, which is a little bit more difficult, and I'm going to have to ask your help for this. Okay, can I get rid of Mr. Smiley Face? Okay, so this is a little bit different. We've got 2 point charges now. Point charge pink and another point charge pink. Come on, I want to get you at the same level. Okay, so quite obviously, hopefully this is obvious. In between these two charges should be a point where the electric field should be dead on zero, because they should cancel out. Now these point charges are at 35 microcoulombs. Let's get a text here. 35 times 10 to the -6 coulombs. Why are you not copying? Oh, I'll leave one of them there. And they're asking if these are 32 centimeters apart, which means that in between the two is 16 centimeters. Oh, that's nice. So they've got a squared number in between there to work with. I bet you there's going to be some squares involved. So it's 16 centimeters or 0.16 meters between that and 0.16 meters there. So I'm going to assume that they're going to be having some squares involved here. Sorry, this is question number 16 on page 489. Okay, now in between there, we are going to stick another charge. It's also positively charged, so what will happen to these points? I want to make it bigger, so that's 30. No, it's not. It's a tiny, tiny charge. Come on, give me a tiny, tiny charge. There we go. Ah, where'd you disappear? Okay, so you have a tiny point charge. I want to move you. Get out of the way. Ah, rubbish machine. I hate technology sometimes. Okay, so you have one charge in the middle there. How much was that charge again? How much was the charge in the middle here?
Hold on. I shall find. 35.
35.
Yeah.
Those are the point charges at the
Oh,
end.
no. That's, no, 0.5.
0.5?
What number? 16?
16. 35 is the two identical ones, and the one in the middle is 0.5.
Yes, 0.5.
Okay. So I can just do that. Would that work?
Mm-hmm.
Okay. So what's happening? What are they asking you to do?
How much work is required to move it from a point midway between them to a point 12 centimeters closer to either of them?
Okay, so let's just work it out in one of these directions. You're moving it that far by 12 centimeters.
12 centimeters closer.
So 0.12 meters closer. So you're getting really close to that surface. Okay, so how would you work this out?
Well, calculator.
Sorry?
We calculate.
Using which equations?
Can we just use the same equation first?
What do you mean?
It's 0.2, 0.12. I don't know. So can we just do like the one we did for the first question that we solved?
So the first question that you saw, you have a distance, you have a charge, and you're working out your voltage. Now, this voltage is going to be different at this point here in the middle and this point there. Now, those voltage differences you can use to work out how much because you have your distance, if you can figure out the difference in force, I think if you take the force at point A and the force at point B and you subtract them, you figure out how much force has been used overall, I think. Well, you have to go to the energy. Let's have a goosey gander. So the example that they give on page 477 kind of wants you to look at work as the difference in the voltage multiplied by the amount of charge. Now you're not moving, assuming that the charge, that the 235 microcoulomb charges are not moving, that they're set, they're stationary. If they don't move, then the 0.5 microcoulomb charge is the one that you're moving, and we're counting the mass as negligible. What you're looking at is you're looking at the voltage change of that 5 microcoulomb charge. So how do you work out voltage? Hint, hint.
From our equation.
Hint, hint, hint.
Give me
How do you work out voltage? Hint, hint. Not Gucci gang. Goodness. Okay, so there's two things going on here. One, as you're pushing the charge this way, you're having an increase. You're having an increased oppositional push over here. As you're going away from this one, you're getting a decreased oppositional push. Okay, so you can't just figure out the voltage change from one point source. You have to figure them out from both point sources. Okay, so your voltage A and your voltage B at point A and point. Ooh, good. Ooh, wow. Sorry, the arm of my chair just came off.
I got 196,000.
All right. Do you want to show us how you did that?
Not really, because I think it's wrong. I mean, okay.
Why would you say why would you say I've got 196,000 if you think you got it wrong?
Yeah, you can, I don't know, can you see that?
Weston, for which one did you find it out? Because the two of them is gonna be different.
I don't know.
How do you get rid of this pink and green? Clear my
Eraser.
viewer drawings. There we go. Hi. Okay. So can someone start me out by working out the voltage? Actually, we know the voltage in the middle here. The voltage in the middle here is very clear. It's 0. Whatever force that this is pushing there and whatever force this is pushing there has to be 0. So whatever we're working out is in reference to 0. So we don't have to work out both. So we can just start by this 12 centimeter over there. So we can work out the voltage. I'm going to see if I can copy this. Okay, apparently I'm not going to be working that out. So my voltage will be equal to KQ on R plus KQ on R. So I'll get 2 of them. What am I? Actually, no, that can't be it, can it? Should I be using the forces? Because I have 2 point charges. There are 2 point charges. So should I be using the force? Coulomb's law. What do you guys think? Use this formula or use Coulomb's law twice?
Coulomb's law.
So you've got Coulomb's law over here. You've got Coulomb's law over here. We could use that and work out the amount of force. Oh no, but you see, if we work out the amount of force, the force is not a linear relationship. Oh, okay. Because we have to use another technique because the force is not a linear relationship, we cannot use a differential here. Maybe we do have to use that KQ on R. Okay. I think you have to use this technique, but we can use a different equation if you want. The other equation you can use is this one, the W equals, that work also equals, work also equals your charge multiplied by your voltage difference. Okay, you can do that, which means you can work directly there, or you can work out your voltage first and then plug it back into the equation later. Either one works. I'm gonna try this way, going from the voltage and then plugging that back into your equations for work. All right, so if I do that, and someone else can go directly to the work equation here. Anybody want to take that? All right, I'll just get started then. So
Charge, Mr. Hendro, for the formula where it's the voltage difference. Is that the charge of the charge that's in the middle?
Okay, so the charge in the middle is what you're going to work out how much work needs to be applied to it. All you're looking in the first step is to figure out what is your change in voltage of the field as you're going this way. Because if you change the amount of charge that you're pushing into that field, you're going to have a different amount of work done. So at the moment, you just want to figure out what is the potential difference of the field right at that 12 centimeter point. So you don't need to work out anything with the charge of the particle that's being moved. You just want to look at the field strengths of the 2-point charges first before you start moving anything else. Work out the stationary ones first, then work out the rest. So I know that I can take the Coulomb's constant out the front, and then I know my charges are 35, and the first one will be divided by, you add them together, 28, 1.28, and then the other one will be also 35, but you're only dividing it by 0.4. Okay, and I'm going to just multiply all of that by 10 to the negative 6. Just get that out there so it's easier to work with later. Okay, V equals K. I'll leave the K as a constant there. Why are you telling me that my temperature is going over? Okay. Got the calculator. 35 divided. 35 divided by 1.28. 1.25, nice. And then I'm going to add to that my other one, which is 35 divided by 0.4, which will be 87.5. Okay, so there's not a huge amount of difference there if I was to just calculate it using the one that's closer. There is a tiny, tiny amount of repulsion. Oh, the vectors. Oh my goodness, I nearly got the vectors wrong. Because it's from the other direction, this is negative. This is negative, which means this is also negative. Okay, so V equals 87.5 minus 1.25 minus 1.25.
So Hinter, why do you put the charge as being just 10 to the negative 6?
I'm not putting the charge as negative. I'm putting the position as negative. So,
Isn't, you know, in the formula W equals Q times VA minus VB, what is that Q? What charge is that?
just give me a 6.25.
Okay.
Sorry, run that by me again. What was that question?
I was just wondering, in the formula work equals Q times VA minus VB, which charge is the Q? Like, is
The small q.
Yeah.
Okay,
Is it
your
one in the middle or is
your small q is the charge that's being moved.
that one, right?
Yep.
5 times 10 to the negative 7.
Yep. So that would be the mass of your object if you're moving it up in a gravitational field. The gravitational field is what we're trying to work out. As you move the position here over to the right, it's not, sorry, not gravitational field. You're trying to work out the electrical field. If you were to move something from the Earth to the moon, as you get closer to the moon, you'll experience more attractive force from the moon than from the Earth. Okay, just because the masses of the moon and the Earth also contribute to this.
So what is that?
This
The
10 to the negative 6.
6.
That's just I just took that out from the charge. So 35 here is the charges.
Oh.
I'm just ripping out the 10 to the 6 because I don't like it in there. Just don't worry too much about it. I just like having the exponents off to the side.
Okay, so where does this go in this equation?
What do you mean?
Isn't that the, are you putting it, oh, I see.
Okay.
Yes.
So so if I know that I'm working out if this point here is B and this point here is A, what I'm working out here is VB. Okay, this is what I'm working out. I'm working out the voltage at point B. We know that the voltage at point A has to be 0. Why do we know that? Because there'll be the equal amount of electrical field pushing in that direction. So the electrical field from this particle will cancel the electrical field from that particle. So I can assume that VA equals 0 or something like that. Actually, it doesn't really matter if it's VA or VB. You just need to know that the total amount of work done, whether it's a push or a pull. Yeah, I don't really mind if you're pulling it or you're pushing it. Just be mindful of the signs if they actually give you a type of movement. Okay, so let's finish this off so we actually have an answer to stick in our book. I'll actually stick VB down here just to keep it easy. So 9 times 10 to the power of 9. Actually, if I add that to the 6, which the 6 will actually be, I can move that over there, and I can make that a 5. And I can get rid of that and make it a 4. So 9 times 8.625. 9 times 8.625 is 77. 77.1. Why do I always close the calculator instead of 8.625 times 9 equals 7765. I'm going to copy you. What did you get for your answer, Weston?
Wrong. I got the wrong answer.
Sorry, 2 significant figures, 2 significant figures. Yeah, I can do 2 significant figures for my result. Times 10 to the 5. Let's fix this. 8.625. Okay. All right. So with this, what you can do then is, you know that your VA minus VB, the difference has to be that much. So I can then stick this into that equation. Work equals your charge quantity multiplied by that. And I can change, I can add the Q in, which is how much? That much. So I can then have work is equal to 5.0 times 7.7 times 10 to the power of negative 2. 5.0 5 times 7.7. Come on, don't be a pain in the neck. 38.5. So my total work should be 0.38 joules. That makes sense? I really hope that I got that right.
Numbers is 16. I can check.
Please check number 16. What does it say at the back?
16 won't be at the back. I have to look up Slater.
Now, what does Slater say then? Actually, check them both.
Because the back only has odd numbers.
Does it? Why don't I just ask odd numbered questions then?
You can check Slater for those answers.
Number 16. It says 2.5 joules.
What?
That's what
Well,
this says.
I'm wrong then. 2.5 joules. Wow, what did I do wrong? I'm off by a factor of... I'm off by a whole order of magnitude. What on earth did I do wrong?
Doesn't our class end soon?
Yeah, it needs to end now. Well, I've given a starting point for this. Maybe if somebody could help me fix up question 16. I'll see if I can save this picture. How do you save this? Save. Whiteboard save, show in folder. Okay, so the whiteboard will save to that particular Zoom thing, and I can open that whiteboard again later. Okay, let's hope that works. Okay, I'm going to stop sharing. At least I hope the idea that I had was correct.
You want to see? I can show you the steps if I screen share.
Okay, please.
Okay, hold on. So, can you see it?
Yes, I can. Question 16 is what we want, isn't it?
Yeah, this is 16. These are all his steps.
What? Okay, so he's got the potential energy there. Oh. Why is he working out the potential energy at the 0 point? Why is he moving the potential energy to the 0 point? And how is his... That's not right.
It could be wrong. Sometimes they are. But
Yeah, because that would mean that if they were both on the same side pushing in the same direction. Yeah, that can't be right.
okay.
That would be that would be, I mean, if one of them was a negative charge, did I read that wrong? An identical positive charge. So at the 0 point, it has to be 0.
It sure is a lot of work for one problem.
No, I'm not.
If you can do it in 2 steps, Mr. Hendro, I'm much more inclined to follow your way.
I don't agree with what he's done here. It seems to be that he's missed out some sneaky ways of going around it. That's
Does anyone feel like we're going to the material really fast? Or
No,
is it just me?
this will probably be the last unit for the year. I don't think.
Are you serious?
Yeah, I don't think we're going to be able to get everything done in time. As in, if we get this done at the end of the week, I'll be amazed.
I'll
Because
be
I
not
felt
be
like
able to do that.
I felt like we went through chapter 16 too quickly.
Yeah.
And it showed in the quality of work that you guys are putting in. I thought, yep, I'm going too fast. So I'm trying to slow it down a bit.
The thing is, it's especially because we're at home, we're doing this by ourselves only,
Yeah,
like individually.
it's difficult to discuss with other people,
Yeah.
especially when you can't write on paper in front of someone else, pass the bit of paper across to another person. All right. Okay, well, I'll leave that with you. And I'll say thank you very much for your time. And for Aiden and Ethan, when you see this, hope to see you again soon.
Thank you.
God bless you all, guys.
Bye.
Bye.
Yeah. Huh? You can speak though. See ya.
He's asking me to join his meeting. All right.
Oh.
See ya.